Hi there, Nick here, M0NTV, and welcome back to my shack and to another homebrew ham radio video. Now, last time you will remember I showed you my pre-driver and my driver amps, and I talked about the importance when we get to these kind of relatively higher RF power level stages of impedance matching. And I said, you know, I thought this was so important, I need to do a separate video on it. Well, I've been down the mother of all rabbit holes on this one, I tell you. There's so much here, way more than I even thought when I announced that. So I am going to do a video on it, and more specifically on how you can, relatively simply, build impedance matching networks on the input and output ports of your amplifiers, and put them anywhere really, because you know an impedance matching network is an impedance matching network. But before we just dive straight into that stuff, it kind of occurred to me that maybe we need to just take a bit of a step to the side for a moment and just kind of review some more basic questions, like what even is impedance, and why do we have to bother matching it in the first place? You know, how do we measure it? I mean, and I think something just kind of reminded me of when I first started out in this home brewing business a few years ago, and very early on I came across the thorny question of impedance, and to be honest, I didn't really know what it was, just that I was told I had to try and match it. I didn't know how to measure it. I just didn't know, and I asked a few people, and I kind of got the impression that they weren't 100% sure either, really, and just said, well, you know, we know what it is, but it's a bit of a dark art, you know. That kind of leads me on to the second thing, really, which is, you know, the reason I build radios is to understand how they work. Right? I don't build radios to get a radio. You know, I could go out and buy a radio. The most important thing for me is not the radio, it's actually the knowledge, it's the education, it's the understanding that I get through building it. And yeah, it's great to have a radio you've built yourself at the end. But once you've got that knowledge and understanding, you can take that and build anything, right? You know, so I mean, it's a really powerful thing. So, and it's that thirst for knowledge and understanding. I want to try and understand what's going on. And that's really what drives me on with this stuff. So with that in mind, this video, and it's probably going to be a part of at least two parts, I would imagine. So we'll get to the actual how you match the input and output ports of your RF amplifiers. But for today, we're going to have a dig into the basics. So I know people watching my videos and subscribers to this channel come in different shapes and sizes. You know, I've got people that are seasoned homebrewers, far more experienced than I am. I know there are people that have done some tinkering with electronics in the past and haven't for a while and have just come back to it. And I know, because they correspond with me, I have some people that are complete beginners, right, to all this stuff. And you're all welcome. You know, and I'm pleased to have you all on board. So I don't want to teach my grandma to suck eggs, but if you know all this stuff, then that's fine. I'll see you on the next video. But if you want a kind of refresher and you just want to maybe just check out this information again, then stick with me. And I just offer this not as an expert, because clearly I am not one. I offer this in the spirit of sharing and helping as one homebrewing ham to another. So with that, I hope you find something of interest here, and I hope you enjoy. So here we go. Impedance, the basics revisited. Now, many of you will be familiar with this drawing, or a version of this drawing, Usually it just features these three, the green one, the kind of browny red one, and the blue one. And of course it illustrates Ohm's law, really. This is the relationship between voltage, current and resistance. And it's quite good, really. So you've got the voltage, which is kind of forcing the current through the wire, whilst the resistance is restricting the flow of current through the wire. And of course, as we will see, this holds good at DC, direct current, and it holds good for AC, for alternating current, except that when we come to AC, as you will see in a moment, it's not just this guy, Mr. R, that we have to concern ourselves with. Turns out there's another force at work which seeks to restrict the flow of current, and this is this mysterious Mr. X over here in his Dayglow pink. I don't know why I did him like that, but anyway, that's how he is. Now, turns out, unlike this guy, as you can see, has kind of lassoed the wire. So any current at all, which is trying to make it through here, will feel the restriction of the resistance. And it's irrespective, because as you can see there, he's tying that. Anything trying to get through there, is going to feel the effects of resistance. Mr. X, however, turns out is far more picky and choosy about the current that he lets through and past him. So, for instance, there is some current which will make it through, and it's almost like Mr. X is not there. He just stands aside and lets it go straight past him and does absolutely nothing. Whereas there's some current that will try and make it through, and Mr. X is just there, right in his face, like a brick wall, not letting anything through. And then there's some current which is, well, kind of in between, will be restricted to various degrees. And the truth is, when it comes to impedance, as we'll see, the headline news is that actually we have to consider not just resistance, but we have to consider Mr. X over here, which is actually reactance. Well, what is impedance? I'm glad you asked. Well, and to kind of help you understand this and to try and keep this as practical as possible, I thought probably the best thing to do would be to run a few simple experiments using LT Spice simulations, so you can see for yourself what the effects are of some of the components we're going to use. So that's what we're going to do now. So the difference that X makes. And I want to show you first of all then, just look at this little circuit up here on the top left. So I've got my ridiculously oversized cursor here, so hopefully you can see what I'm pointing at. So all we have is we have a 1 volt voltage source, and this is an ideal voltage source, so there's no resistance at all, it's just 1 volt. Going through a 50 ohm resistor, and that's going into a load which is also 50 ohms. Now, this is about as basic as it gets. So if I show you this, if we put the little probe in here, so we've got 1 volt, which you would expect to see, and if I take the probe here in between these two resistors, you will see we have 500 millivolts, so half the voltage. Now that shouldn't come as a surprise, because of course what you're looking at here is one of the most fundamental and important circuits in electronics. It is a voltage divider, and I can't tell you how many times you're going to come across a voltage divider. I mean, just so often. Very, very useful thing to get your head round. Now, there is a formula for determining how much voltage falls on each of these resistors. Now, of course, in our instance, we don't need to do any of that because it's blatantly obvious, because they're both two 50 ohm resistors. So clearly the voltage, half of it's going to fall here and half of it's going to fall here, because those resistances are equal, and which is exactly what we're seeing over here. So so that is your basic DC voltage divider circuit. Now, if you look over to this side, this is an identical circuit, 50 ohm resistor, 50 ohm load, except this time I've taken out the 1 volt DC voltage source and replaced it with a 1 volt peak 10 megahertz sine wave. So we've got an RF signal going in here. Now, so if I took a measurement here, there we go. So there's our 10 megahertz sine wave, and you'll see it's 1 volt peak. Now, in a real life situation, you probably wouldn't be able to do what I've just done here, because to try and keep these circuits the same, what I have done is I haven't given this signal any characteristic impedance. And that's what this resistor is doing, in fact. So if we were building this circuit in real life, and let's say this was we were using a signal generator, the signal generator would be this and this, right? So this resistor would be part of it. This is the characteristic impedance of our signal. Okay, I've just expressed it separately. I could have just put 50 ohms in here, but I wanted you to see this because I want you to see the similarity with the DC circuit. So if we had the output port would be here. Now, it doesn't have to be a signal generator. This could be the output of an amplifier that you've built, or an oscillator, whatever. But the point is, this is the output here, and this is going into our load. And so, if we were to do the same thing and take the voltage here, okay, this is in blue, I'll just put that one up there, 500. So half. So you see what's happened here. So the voltage divider is working at AC as it's working at DC, and that's because a 50 ohm resistor is a 50 ohm resistor at DC, and it's a 50 ohm resistor at 10 megahertz, right? It doesn't make a difference, right? A resistor is frequency independent. I mean, I know if you're going to get into microwave stuff and very high frequencies, then that starts to break down. I understand that. But for our purposes here, and certainly at HF, a 50 ohms resistor is a 50 ohms resistor. So it makes no difference. So this is, if you remember that picture, you know, the resistance stood on top of the wire with his lasso, just restricting it all equally, no matter what's passing through that wire. Okay. Now, I want to show you a different circuit. Now, have a look down here at the middle. So now we've added a component. So now we've got the same thing. This is DC again. So it's all DC on the left-hand side and AC on the right-hand side, okay? So we're back to DC. We've got a 1 volt DC voltage going through our 50 ohm resistor again. But now look, we've put an inductor in. A big one, 1 millihenry. Very often in RF work, we're working with microhenries or nanohenries. But we do see bigger ones, and this is a larger inductor, 1 millihenry. Now, we're going to do the same thing again. So if we were to do this, so we've got 1 volt there, yeah, that's what we'd expect. We're going to just take the voltage here, 500. Ah, interesting. So that's before the inductor. We take it after the inductor, and you'll see it's just slightly, it's this green one here, it's just slightly less, and that's because there's a tiny little bit of resistance in the windings of this inductor, but essentially it's the same, really. You know, that's just a tiny amount. So really, this inductor is almost invisible in this circuit, and that's because at DC, an inductor really just looks like another bit of wire, which when you think about what an inductor is, it kind of is, isn't it, really? You might have a moulded inductor, in which case you can't see the windings, or you might wind your own inductor on a toroid, or maybe just an air core inductor. But all it is a bit of wire coiled up. And so there's a clear DC path through it, so it's not surprising that we get very little resistance to current flow through that inductor at DC level. But, and this is where it starts to get interesting, let's now take this same circuit and do the same thing. So swap out the DC voltage source for our AC signal source. So now we've got our 10 megahertz sine wave again, this time going through the 1 millihenry inductor. So if I do this here, that's the 1 volt, and we check it here, it's the same. Oh dear. Now if you think like that voltage divider, you know, and where here we were dividing the voltage and dividing the signal equally, here we've got the same signal there as at the source, which must mean that from here on in the circuit we're seeing a much greater restriction to the current flow than we are in this 50 ohms resistor, because it's like it's not even there. And sure enough, if we actually do the test here, look at this, nothing. I mean, if you want to go around, it's actually 0.8 millivolts peak, but compared to here, it's nothing. Virtually nothing is getting through. And to help you understand why, the best thing to do is to have a look at this in the frequency domain. So I'm just going to swap these statements over here. And okay. Yeah. So look at this. This is your classic low pass filter. This is the effect. So this is frequency down here, and this is the power of the signal going up the y-axis here. So you can see now. Here's our 10 megahertz signal right down here. Where are we? Look at that. Over 60 dB, which is a lot. So, and in actual fact, if we look here, so where are we at? We're at about 7 dB or something. So minus 10 would be the 3 dB point. Yeah. So you can see here then anything above really about 16 kilohertz is going to really start to be seriously attenuated. And you're seeing now the effect of inductive reactance. That's what this is. It's like this inductor is acting a bit like a kind of frequency sensitive resistor. So it's I don't want to say resisting, because it's not, that's a resistor, but it's restricting. Let's use that word because it's a bit more neutral. It's restricting the flow of current based on the frequency of that signal. And you can clearly see that because all the low stuff, so that's why all the DC goes through, because it's absolutely fine, looks invisible practically. But the higher up you get to this point, where actually then the higher the frequency, the more and more it's the current is restricted and attenuated. And I'm just going to show you now what that looks like on a chart. So this is a chart indicating how reactance changes with frequency. And you can clearly see here that at very low frequencies there's very little inductive reactance. But as the frequency increases, so does the inductive reactance. It gets higher and higher and higher. Now the formula for calculating inductive reactance is 2 times pi times the frequency times the inductance. And the inductance is in henries. And the frequency is in hertz. So you need to make sure you've got the right amount of zeros or point zeros on your calculations. Now, what's happening is that inductor is behaving differently. It's exhibiting a different amount of reactance, which is measured in ohms, depending on the frequency of the signal that is put through it. Okay? So now, I'm not telling you anything you probably don't already know with this, because a 1 millihenry inductor, most times when you come across a 1 millihenry inductor, you'd call it a choke. We would have a 1 millihenry choke, and because it chokes off RF, and you can see why. I mean, it chokes off RF, very effectively, and you would use one of these perhaps, and perhaps you've used them in your amplifiers, particularly power amplifiers, to keep the RF off your power line, because you don't want RF getting into your power line and getting ripple on the power supply. So, but you want to allow your voltage, obviously, the power to get through, and so that's why you would put something like a 1 millihenry choke on that power supply line, because it will do that. The reactance means that it will choke off pretty much any of your RF and will allow your lower frequency, and you can't get any lower than DC, through. Right, let's have a look at the capacitor. So same thing, we're back to DC again now, 1 volt going through a 50 ohm resistor. Well, let's just change this back first of all, to otherwise we're going to be getting this wrong. This is very hard to do with such a large cursor. Okay, so if we go here, okay, so we've got 1 volt, and if we go here, 1 volt. Well, that's not surprising, is it? And if we go here, nothing. It's down the bottom here. Because, of course, what we've got here is the same circuit again, but this time we've got a 100 nanofarad capacitor in. And, of course, I mean, what is a capacitor? If an inductor is just a coil of wire, a capacitor really is just 2 metal plates with a gap in between. And sometimes that gap is filled with something, a dielectric of some nature, paper, air, a multitude of different things. But the point is, there is no DC path through a capacitor. So it's not surprising that when you put a capacitor in, you don't get any current flowing through. Now, we know about using DC and a capacitor, and you will get some DC going through first as the capacitor charges, but when the capacitor's charged, that's it, current stops flowing. So you're not going to get anything coming through there. But let's do the last little experiment here, and this is where we've got the same 100 nanofarad capacitor, but with our 10 megahertz signal source again. So now we're going to do this here, so that's the 1 volt there. We're looking at this one here. Oh, look, 500 millivolts, 500 millivolts. So it's almost like the capacitor is not there. That AC signal is passing right through that 100 nanofarad capacitor. And if we flip it around, again, it's probably an easier way of doing this. I haven't quite worked it out yet. I keep discovering new things about LT Spice. Right, okay. So, marvellous. Let's just clean that up. And as for the series capacitor, we're seeing a high pass filter. We can see clearly here. And you can see that, you know, you've got to really get up to about, well, yeah, about 80 odd kilohertz before signals will pass through pretty effectively. But once they do, so all our RF signals and HF signals will just pass through pretty much unattenuated, but all the low frequency is including audio frequencies, which are low, and of course DC, which is the lowest of the low, will not make it through that capacitor. Which is why, and I'm sure you'll have done this as well, if you've ever built like a transistor amplifier and you've put on the input and output, you've probably put a 100 nanofarad capacitor. We call them coupling capacitors or DC blocking capacitors because that's what they do. Because we don't want DC bias upsetting our transistor amplifier. So we put a 100 nanofarad capacitor on the input to stop any DC making it through, and we put one on the output so that we just get the signal and not any DC. So that's another way, a bit like we used the inductor as an RF choke. We can use this high value capacitor to allow our RF signals through and to block off the lower frequency audio and DC. So let me show you the next graph. So this is capacitive reactance, and the formula is down here. XC, capacitive reactance, equals minus, we'll come back to that, minus 1 over 2 pi FC. And with that 1 on top there, you'd be right in thinking that what we're dealing with is the kind of opposite of inductive reactance. So this is capacitive reactance. So if we look at the frequency, at very low frequencies, you'll see there's a very high capacitive reactance, which is why DC doesn't make it through, which is why our low audio signals wouldn't make it through our 100 nanofarad capacitor. We'd need a much larger capacitor to get those through. And as we increase in frequency, note the actual capacitive reactance goes down as we increase. And so it's really the opposite of what we saw with the inductive reactance. Now, if I show you this graph here, sorry it's not very clear, this one, but all this basically does is just superimposes the two. So that's the inductive reactance, the XL going here, and that's the capacitive reactance we've just seen here, and you'll see they cross. Now where they cross, let's say for instance this is 10 ohms on here, okay, 10 ohms of inductive reactance. So here's the inductive reactance going up here, 10 ohms. But this is on the same scale. So this capacitive reactance must also be 10 ohms, or more correctly, it's minus 10 ohms. And what this means is, because you've got 10 ohms of inductive reactance at this point, and you've got minus 10 ohms of capacitive reactance, that equals 0. 10 minus 10. So they cancel each other out. And the point at which they cancel each other out is known as the point of series resonance. And you can have a parallel resonance as well. And of course, this cuts to the very heart of radio. It's tuned circuits, it's filters, it's everything. And even really, I mean, it cuts to the heart of the fundamental forces of the universe, really, because you're talking about a capacitor which stores and releases energy from its electric field, and you're talking about an inductor which stores and releases energy from its magnetic field. Well, that's electromagnetism. You know, I mean, this is pretty cosmic stuff we're dealing with here. You know, it doesn't really get much more fundamental. And this is the magic of it. There is a frequency there at which they cancel each other out. And this is really significant. Now, so what impedance actually is a complex term. Now, when I say complex, I don't mean complicated. I mean, it can seem complicated, but I mean complex in the technical sense of it consists of two different parts. So the two different parts of impedance are, first of all, a real resistive part, which is the resistance, and then a so-called imaginary reactive part, which is the reactance, and that's represented down here. And so that's what we have. So let's imagine that our real resistive part is 50 ohms, because it very often is in RF electronics. We've got a 50 ohms resistance, and we've got a reactance. So if we've got a reactance of, say, an inductive reactance of 10 ohms, we would write that as 50 plus J10. Now, why J? Well, it's because we're getting into vectors here, and in mathematics, I believe they would use I, the lowercase I, to talk about vectors. But to differentiate that, we use J in electronics. So we would talk about 50 plus J10, or 10J. So what that means is 50 ohms resistive plus an inductive reactance, because it's plus J10 of 10 ohms. Now, let's say we had 50 ohms, but we had a capacitive reactance of 10 ohms. So 50 ohms with 10 ohms of capacitive reactance, that would be written as 50 minus J10, or minus 10J. And that is how impedance is represented. Now, the truth is that in any RF circuit you're going to build, you will be dealing with complex impedance. That's what I mean, is you will be dealing most probably with real resistance and with inductive and capacitive reactance. Now, some of that will be intentional. You know, you'll put a real resistor in because you want some resistance, you want to control the current or get a certain voltage at a certain point in the circuit. Some of it will be resistance that you hadn't bargained on, just because wires have resistance and devices that you use exhibit resistance. And the same with reactance. Some of the reactance you put in will be planned. You know, you will put in a capacitor to block the DC, right? Intentionally. You will put in perhaps an RF choke to choke off any RF getting into your power line. But some of it will be unintentional. You know, there will be straight inductance, just the lead lengths of your components. You know, there will be straight capacitance everywhere. Even funnily enough, when you're building an inductor, if you wind a toroid to build an inductor to get some inductive reactance, you'll also end up with some capacitive reactance, because those little windings act as little mini capacitors, and so you'll get some straight capacitance there. So basically, we're dealing with impedance all the time. And really, the best thing is that actually inductive reactance will cancel out capacitive reactance, and vice versa, because one is positive, the inductive reactance, and one is negative, the capacitive reactance. And so really the goal of all impedance matching is to try and cancel out that reactive element. So that's to say, if we've got a circuit that ends up with a positive inductive reactance, we might use some negative capacitive reactance to cancel it out, and vice versa. So the aim is to get to zero reactance, to cancel all that stuff out, so that all we're left with is a pure resistance. And if that resistance is about 50 ohms, then fantastic, you know, we're a one-to-one SWR around there. So that's the goal, and that's what we're going to be looking at in the next video. But for now, I just want to very briefly just address two things. One, just very quickly, is why are we bothering even doing this stuff? I mean, why bother matching? What happens if we don't match the impedances, right? And secondly, just the way that I measure impedance. It's not the only way. I'm not saying it's the best way, but it's the way that I increasingly will use these days. So on with the rest of it. So why bother matching impedance? And you might say, well, I've built some audio circuits. I never had to faff around with all this impedance matching. Matter of fact, you didn't want to match impedance, you know, and that's true for a lot of audio circuits. The kind of rule of thumb is that you would make sure that the input of the next stage of your circuit had an impedance, an input impedance, at least 10 times higher than the output of the last stage. So you're always feeding into a higher impedance, which will give you you know, more voltage in the next stage. The reason we do it at RF is for maximum power transfer, because the maximum power theorem states that you get maximum power transfer when impedances are matched. So that is to say that the output of one stage is matched to the input of the next. And if you can do that, you will get the most you're going to get. And the most you're going to get is 50% efficiency. And that will mean the lowest voltage standing wave ratio, which will mean less signal reflected back, where it's just going to mess around with other things, and it's just wasted basically. And so that's why we try and match impedances at RF. So finally, how do I measure impedance? Because it's all very well talking about going on to match it and stuff, but how do we know what it is anyway? Well, this is a huge topic in and of itself. There are lots of different approaches to it. One way that I would advise is to go and check out Alan Wolke's video. Well, go and check out his videos anyway, because they're brilliant. But W2AEW, his YouTube channel, he's got a great video on different methods that you can use to measure impedance. You can try the LT Spice route and actually kind of simulate your circuit, and there's some good ways that you can measure impedance there as well, and that's very useful as well. And again, you know, I'd need to do a separate video on that really. But I've got to tell you, these days, for the money, the way that I would do it every time, all day, every day, is the Nano VNA. And this is a very old one. Actually, I've got a new one coming actually for my birthday, so I'd be interested to see how that performs. But this little boy, I mean, you know, he performs so well, and they're great. And for things like impedance measurements and SWR measurements, they're absolutely fantastic. The great thing about measuring impedance and SWR is that you don't need a lot of power, and you only actually need the well, what they call the channel naught on here. You're going to do an S11 sweep with this. So what I would do if I was measuring the impedance, let's take an amplifier then. So I'm going to measure the input impedance of the amplifier. What I would do is I would connect the S11 port. I'd calibrate this all first, you know, as usual. I'd connect this to the input port. I would put a 50 ohm load on the output port, and then I would power it up. That's really important, particularly if you're using active devices. You'll get a very different results if you do it with no power attached and if you've got no load on the end as well. So you need to put a load on the other end. You need to power it up, and then you can read it off the Smith chart, and you can look at the SWR, and there's a whole host of other stuff as well, and that will give you a really good indication of what the impedance is. And then for the output, all I do is I just swap the lead over. So the lead from here now goes through to the output. I put the 50 ohm load on the input of the amplifier, power it up again, and do the same. And so that will read the amount of reflected signals coming off that output port. And again, that seems to work pretty well. So this is a real game changer for so many reasons when it comes to building your own radio. But for me, I find that one of the most powerful tools at our disposal. So well, there you go. Bit of a different one this time, but I hope you found something of interest and maybe clarified something in the wonderful, mysterious world of impedance. But next time, we're going to be taking all this stuff, putting it into practice, and designing and building some LC matching networks for our RF amplifiers. So thank you ever so much for watching. Please like and subscribe, and I will see you on the next video. But until then, look after yourself. 73. Bye bye.